Today we're going to start our new unit. It's called the Uniform Circular Motion. This is going to be used quite a bit on our field trip that comes up in a week and a half, in addition to the stuff that you've just learned on conservation of energy. That's going to be one of the other major topics that you're going to use while we're on our field trip, riding roller coasters. You can imagine, if we're talking about an object that's undergoing circular motion, okay, that's a thing that you see on roller coasters quite a bit, right? Roller coaster cars going down a hill and then going in an upside down loop, or even just going around in a horizontal circle. Okay, that's circular motion. When an object goes in a circle, it's called circular motion. Now, uniform circular motion specifically is when that object is going at a constant speed in circular motion. Sometimes an object is going in circular motion, but it's speeding up or slowing down. We'll solve problems where the speed is constant or where we can pretend the speed is constant, and it still gives us a pretty reasonable answer. Uniform circular motion, object going in a circle at a constant speed. We're going to define three terms here today and provide three equations that go with those terms, and then that'll be the day for us. The first one is frequency. Where have you heard that word before? Give me a sentence with the word frequency in it. Okay, the radio frequency is bad. So what does that mean in that context when you've got a frequency for a radio? Okay, so frequency is not the connection, but sometimes you do get a bad connection, obviously, and sometimes the frequency is off. You get white noise. How tuned it is, okay, how tuned it is has to do with waves in the context of a radio. Have you heard it in any other context?
Simon's homework frequency is good.
Okay, Simon's homework frequency is good. Okay, so
He's also very helpful.
so what do we mean by frequency in that context? Simon's homework frequency is good, or as Simon likes to say, excellent. What does frequency mean then? That he does it often, that he does it lots of times per semester, right? Frequency means regularity, yeah. Yeah, he does it with regularity. Okay. Frequency is defined in the context of circular motion as the number of revolutions. You said, Simon, you called it regularity? How often something happens? The number of revolutions per unit time. So Simon has a number of homework completions per semester. Now we're talking about the number of revolutions per unit time. Usually it's per second, by the way. The symbol for frequency is a lowercase f. Can't be a capital F, because a capital F would be what? Force. And we're going to use force in this unit. So we don't want to get mixed up between frequency and force. Let's make sure we make force capital F. Let's make sure we make frequency a lowercase f. The equation that we can describe frequency with would be simply the number of revolutions over the amount of time. When you look at that equation, what do you think the units might be? Seconds and revolutions. Number of revolutions. But we're going to say it opposite to that, right? It's not seconds per revolution. Rather, it's revolution per second. Does that make sense? There's another set of units that means exactly the same thing as a revolution per second. You may have heard it before. Talk about the radio and the frequency of the radio. Might jog your memory here. Anybody got it? Same thing that means a revolution per second. Nobody's got it, hey? That hurts me that you guys haven't come up with the other unit for this yet. It really hurts me actually that you guys haven't come up with the other set of units that means the same thing as a revolution per second. Like so much so that like it mega hurts me that you haven't come up with the other units. What are the other units? How about hertz?
Hey.
How about hertz? 1 HZ. HZ, 1 HZ is exactly the same thing as 1 revolution per second. Isaiah's radio thing with frequency, usually you see on a radio it's measured in either kilohertz if you're talking about AM radio and megahertz if you're talking about FM radio. Kilohertz uses thousands of hertz and FM radio uses millions of hertz. Okay, but the base unit is still a hertz or a revolution or in that case a wave per second. Period is exactly the opposite of frequency. Exactly the opposite, exactly the inverse of frequency. If frequency is the number of revolutions per unit time, then period would be the time per revolution. The symbol for period would be a capital T. Not a lowercase t. A lowercase t represents any time. And a lowercase t, in fact, could represent period because it's any time. But if we want to specifically talk about the period, then we give it its own symbol, which is a capital T. Do you know what the equation for period would be? We wouldn't say seconds over rev, that would be the units, but the equation would be time over the number of revolutions. And the units, Jack, would be? Seconds over revolution. You know what we often do for this? Instead of saying seconds per revolution, we often just say seconds. Technically, it probably should be seconds per revolution, but we can say seconds and get away with that. Now, there's one more equation that relates the period and the frequency together. If frequency is rev over time, and period is time over rev, then the period would be equal to what? Relating frequency to it. One over the frequency, the inverse of the frequency. Period is still going to be measured in seconds. Frequency is still going to be measured in revolutions per second or in hertz. It's actually this equation that appears on your data sheet for period. Now, of course, you could rearrange that and say F is equal to 1 over the period as well. Finally, one more thing, and then that's where we'll leave it. We're talking about uniform circular motion. We said that means an object going in a circle at a constant speed. So let's talk about the speed for a second of that object going in uniform circular motion. If it's a uniform circular motion, then the object is going at a constant speed. So we can describe it by v is equal to delta t over delta t. Not by displacement over time, but by distance over time. When an object goes around in a circle, it is not traveling at a constant velocity. It is traveling at a constant speed. Can you explain to me how we can say that it's not traveling at a constant velocity, but it is traveling at a constant speed? Good. Velocity is a vector. You're changing direction. Remember we said early on in physics 20, like the second day, we said speed and velocity are the same thing, except one has direction, unless we change direction. We change direction, speed and velocity are different things, right? Okay, here we're talking about constant speed. We can do that because the direction is changing, but the speed stays the same. The value, the magnitude stays the same. The direction changes. We can't talk about constant velocity here. All right, I don't want to use this equation though. I want to tailor this equation to this concept, this whole idea of uniform circular motion. Tell me this, how far does an object move, any object move, as it goes around a circle once? Nope. The displacement would be 0. The distance would be what? The circumference. And what's the equation for the circumference of a circle? Pi times d or 2 pi r. Either one. Now, some of you, just as a little aside here, some of you probably get 2 pi r and pi r squared mixed up. Anybody ever find they get those mixed up? Hey, when I was in high school, I did all the time. And then one day, I just had this epiphany. One day, it occurred to me, this is how I remember. 2 pi r gives me units of meters. Pi r squared gives me units of meters squared. Well, meters squared is going to be area, and meters is going to be circumference, right? So then I never forgot it again after that day. I don't know why it took me so long to figure that out, but 2 pi r is the circumference, the distance around the circle once. What's the time around the circle once? What do we call that? The time around the circle once. The time for one revolution. That's the period. So we're going to say the equation becomes 2 pi r over t. Let's write that out again. And this is on your data sheet under uniform circular motion. V is equal to 2 pi r over t, which is really just a special form of V equals d over t, but tailored uniquely to uniform circular motion. Let's do one quick example, and then we'll call it a day. The example is on page 250, so you need to download chapter 5 if you haven't done that already. It says the hard drive of a computer stores data on a thin magnetic platter that spins at a high speed. The platter makes one complete revolution in 0.00833 seconds. What's the frequency in hertz and in, what does RPM stand for? Revolutions per minute, yeah. So what do we got here? We've got something at 0.00833 seconds. What is that? One complete revolution in that amount of time. That'd be the period, the capital T. We want to solve for frequency, so let's solve for f. T is equal to 1 over f, or f is equal to 1 over t. All I need to do is take the inverse of that. I think when you do that, it works out to be 120 hertz, or 120 revolutions per second. Okay, that's the frequency in hertz. Now, if I've got 120 revolutions in 1 second, how many revolutions would I have in a minute? Divide by 60, you get 2. Does it make sense that you get 120 every second, but only 2 in a minute? So it must be times it by 60. It's okay to guess wrong, right? As long as we stop and think, does our guess make sense? So let's time that by 60, because there's 60 seconds in a minute. We get 7.20 times 10 to the 3 RPMs. This is, by the way, a really common frequency for a hard drive spinning in your computer. 7,200 revolutions in 1 minute. You can understand maybe why hard drives tend to crash sometimes. You got your computer on for hours at a time, and every time you go to access it, it spins 7,200 times per minute. There's going to be a lot of friction there. And sometimes there's going to be electric charge buildup, and sometimes that electric charge discharges and wrecks everything. If you drop your computer, what happens? Well, if you've got this little magnetic platter that's spinning at 7,200 revolutions a minute, and that platter is off by the slightest little bit, it's been displaced by the slightest little bit, then it's going to be wrecked pretty quickly when it's spinning 7,200 times per minute. By the way, you can buy hard drives that spin faster, right? 9,600 RPMs, even more. What would be the benefit of that? They cost more. What would be the benefit of having? When you access data from the hard drive, as it's spinning around at 7,200 RPMs, the information is stored all over the place, right? It's not like you got this disk and they use one little spot on the disk and then they use the spot next to it and then the spot next to it. It's in random places on the disk. And when you go to access something, it spins to the spot basically where it's needed. Now it's spinning pretty fast, 7,200 RPMs, right? But if you have a disk that spins faster, then your access time is going to be even faster, right? If it spins at 9,600 RPMs, then your access time is going to be, what, 20% faster than if it's at 7,600 RPMs, which if you do a lot of work, especially graphics work or anything, then or videos, right, multimedia stuff, then that becomes pretty noticeable, right? Gaming, yeah. Does that make sense?